Right now, today's Wednesday, and I've got this lab hopefully pretty set up. Not too much more time to set it up, maybe another hour or two. And in class, if you were a green group, you've already seen me do this stuff. If you're a gold group, we're going to talk about this when you're in, and I'll show you some stuff. I'm preparing silver nitrate, so I want to go on from here assuming that you know or will know about our silver nitrate production process. This has been a very engaging process for me. Okay, and then we're going to talk about some redox. So that's not the focus of this video, but we're going to do redox remotely. We're going to do balancing redox reactions remotely. So after this video, which I think is 26C, get into the other ones. Because we can do that remotely, that's class stuff that we will. That's just problem solving. Okay, and there was more information about our silver nitrate production process, and that will be completed. That's not all the way done yet. Okay, so this is there was a couple of mistakes in here I had to clean up. This is using Tolland's reagent to test for the production of a carboxylic acid from an aldehyde. And this was developed by Bernard Tolland, a German chemist. And the Tolland's reagent is a complex ion. So unless you heard me mention this the other day in the green group, you haven't seen complex ions. It's just an ion that's a group. Okay, so if you have an ammonia molecule and another ammonia molecule and they're on either side of a silver ion, the silver ion is still doing its thing. In fact, in this reaction you see the silver ion, but it's carrying these along. Okay, and in solution it's stable as a complex ion. When the actual reaction happens, it's just with the silver in this case, but a complex ion. You see complex ions a lot. I think last year we did activity series reactions, and where we put a metal in a salt solution to see if it would react, and we made predictions on that. Pretty sure we did that lab. It was probably the first lab we did, maybe the second. And if you do that with aluminum and it reacts, it tends to make aluminum ions, of course, but they get up in the solution and maybe grab carbon dioxide out of the air and they make complex ions, and they tend to be gummy solutions with aluminum stuff. So we may have seen that in class. What we're studying, though, is a redox reaction. An oxidation reaction and a reduction reaction, they always happen together. So in our case here, and this is a more complicated version of ones we'll be balancing equations for, it's a more complicated version than making the silver nitrate. Our silver ion will gain an electron and be reduced to solid silver, and the glucose, which is also called dextrose, its blood sugar, will be oxidized to gluconate ion, which is a carboxylate ion. In other words, it's carboxylic acids. It's a carboxylic acid minus the hydrogen, so it already gave the hydrogen away and it'll make an ion. So we can interchangeably talk about the carboxylate ion and carboxylic acid. It's just a matter of whether or not it's in an acid or a base environment, and whether or not the hydrogen is sticking to it. So the Tolland's reagent does not test for the presence of an alcohol or a carboxylic acid directly. You couldn't, for example, put the Tolland's reagent in a carboxylic acid, nothing would happen. It will, however, take an aldehyde and consume it and turn it into a carboxylic acid, in which case you knew you had an aldehyde. And the only way you still have aldehyde is if when you started you took some out and reacted it, and the remainder of it's in the container. So it tests for the production of a carboxylic acid from an aldehyde in chemical reactions. The Tolland's reagent must be made fresh, it's used, and then the excess must be chemically stabilized. This happens in a basic environment, the reaction we're going to do with the Tolland's reagent. So when you're done, you have to dilute that solution, neutralize it with dilute acid. Because if you leave it sit around for more than a few minutes, it will degrade into silver nitride, which is a contact detonator. In other words, it explodes. It doesn't explode, it's a much quicker reaction than that, it detonates. So it also detonates violently when exposed to concentrated acid. So when we're done with the reaction, it's your job to remind me to neutralize that so I don't forget. Otherwise, we blow up, okay, which is not a good plan. So this is a chemically basic environment. It's a little, we're not gonna, come off with limbs missing, but you don't want to, we're not gonna use that much, but so you don't need to, notify FEMA or anything. But we do have to pay attention to what we're doing. It's small amounts, but you don't want a bad surprise. The reaction is to take ammonia with the silver nitrate I made, or we made, or you watched me make. This was actually a much more dangerous process probably than that because of the nitric acid we were using. Make silver oxide and water and ammonium nitrate. Now that the silver oxide is made in this basic environment, it's going to grab another ammonium hydroxide, and make the Tollens reagent, the silveramine, or silveramide ion. Now I've got an OH stuck on there, so it's if you take that OH off, you have a positive ion. That's a diamine. And water. Okay, so if that OH comes off, you have the soluble Tollens reagent, the silveramide, or diamine silver ion. That's the Tollens reagent. Okay. Now let's talk about glucose a little bit, which is going to get oxidized. Something happened here. Where's my big page? Here we go. I want to remind you from physical science class, I know you talked about this, that as oxidation is losing electrons, reduction is gaining electrons. And you may remember that I know that you were taught the mnemonic oil rig, or Leo the Lion says grr if you want to do it the other way. Okay, so let's talk about glucose a little bit. It's the sugar that's in blood sugar. It actually spends the vast majority of time in this cyclic form. And you can break the bonds. I guess it'd be right here. Right there. I think you break this one. Yeah, if you break this one, it can form this linear molecule, chain molecule. It spends the vast majority of its time this way, though. Now, when this reaction goes, this is the one that's going to react. That's okay, because if you have a million of these, and one or two of them break like this, and then it goes back to cyclic, you can still access them while they're there. So the reaction isn't quick, especially when it's cold, but there's enough there for it to go. Now, don't think that this is resonance, because it's not resonance. We're not talking about electrons that can seem to exist in more than multiple places at the same time. This is actually a shape of a molecule, changing shape to another form, and then changing shape back. That's not resonance. So if we take this one, which shows up once in a while, I want to give you some more information. Notice this is D-glucose, and we don't have time to get into it now, but the D has something to do with the way that it optically rotates. If you use a couple of polarization filters and send light through it, it either is going to rotate the light rays to the right or to the left, and that's beyond the scope of what we're doing right here. But the kind that's in you and in nature that plants make and that we consume is D-glucose. There is another glucose called L-glucose, looks like this one. So this is the one we're using. You wouldn't be able to get energy out of here because the OH is on the wrong side. And we are going to talk about something called enantiomers. That's not what we have here, by the way. But an enantiomer is when you have, for example, and this is, I think, the first time I've mentioned it, so let me give you a real basic idea. An enantiomer is when you have a molecule that's got a right-handed version and a left-handed version, and they're exact opposites. You can't superimpose them. If you try to take a molecule that looks like this and send it through an enzyme to do some biochemical reaction, but you got the wrong one, it's not going to fit in the glove. It's not going to fit in the receptor. That is not what's going on here. I'm pretty sure these are not enantiomers. I'd have to work it out, but I'm pretty sure this is not an enantiomer. Everything would have to be reversed in order to do that. So don't think that this is an enantiomer sometime when you get done with the course. Another thing we're going to be talking about coming up is carbonyls, and I think I'm going to wrap up with this one and get into the mechanism next. I'm not sure. A carbonyl is anything that kind of has, you don't know what's here, and you really don't know what's down here. So here are 3 examples that you should have memorized from your flashcards. You have carboxylic, I don't have lone pairs on these. You have a carboxylic acid, and if this hydrogen comes off, you've got a carboxylate. We've got an aldehyde. Instead of having an OH there, it's an H, or a ketone. And in this lab, we are turning, the Tollens reagent will convert aldehyde and carboxylic into carboxylic acid in a series of multiple steps, and then it'll be destroyed in the process, most of it. We've got to get the leftover, remind me, to neutralize it. Yeah, I think we'll cut this video off here and put the rest of it on another one. Nope.